So my name is Richard Campbell. I make a lot of podcasts. This story actually is partly because of those darn podcasts. I think there's a few .NET Rocks listeners in the room. Awesome. Thank you. My friend Carl Franklin started .NET Rocks back in 2002 before the word podcast existed. And I'll run as is my exercise of my IT brain. I talked a bit about the tablet show last talk, which was the show we made because we weren't sure if .NET rocked. And then it turned out that we rocked after all, so we put it back in. But really, this is about the Geek Outs. So the Geek Outs started because of the last shuttle landing in 2011. I was on the phone with Carl. We weren't recording it. And I was watching Atlantis land for the last time. And I think I went on a 25-minute rant about everything that was wrong with the space shuttle and what a colossal, while it did some remarkable things, it was very problematic, not the least of which killing 13 people in the process. And Carl said, we should record that stuff. And I'm like, for what? And he said, well, I think people would really like to listen to it. I'm like, okay, but you don't put it on .NET Rocks. That's for developers. It's like, developers like space stuff, man. I thought it was a terrible idea, and turned out I was wrong. So we made one. I figured I'd be told to, keep in my lane. But the main response we got from the listeners was, could you talk about this? Maybe this, one of these. So we did another one, and they have to do this and do that. Anyway, I made a bunch of them. There's about 100 now. This is back when we were publishing 3 shows a week. And so every month I would do one based on whatever folks wanted. The space ones are always fun for me. I'm fascinated by all of those subjects. We did a lot of alternative energy. Making a show about whiskey is kind of shooting fish in a barrel. The single most difficult geek out I've ever made was the antibiotics one, because it's much more medicine sort of. I actually crammed a couple of medical training guides on antibiotics to be able to speak coherently about antibiotics for an hour. But a few of them have led to interesting things. And one of them was the moon-based geek out that we did back in 2017. That was based on European Space Agency's paper about very seriously talking about we should be able to establish a base on the moon, preferably the southern pole, that'll be occasionally man-tended to do research. They don't have any of the money for it, but it was a serious proposal. That's largely what that talk was based on. And that was fun, put the podcast out like we did all the time. And later that month, a couple months later, got an email from NASA, which I thought was a prank, so I threw it away, not a big deal. And then they kept emailing me, and eventually that does really say at nasa.gov. And they were saying, hey, we really like your moon-based geek out. I'm like, well, thanks, that's cool. And of course, they only know me as a podcaster, so they ask, would you ever do a presentation about the moon? I'm like, yeah, okay, fine. Just based on the podcast, I mean, sure. It's like, could you make PowerPoint? We like PowerPoint at NASA. I'm like, yeah, Chuck, I could probably do PowerPoint. That'd be all right. And he's like, well, great. Let's figure this out. And I'm like, okay, well, who am I talking to? Like, well, us. What? It's your stuff, right? Yeah, we know. Like, we like the way you tell us. So you want me to talk to you about your stuff? All right. So later that year, I got to go to the NASA Ames Research Center, which is south of San Francisco. That's on the big entry banner was this moon gateway to the solar system. No, it was a good day, let me tell you. My mother is proud. Tough crowd, though. Tough crowd. A couple of chief scientists, a couple of engineers, guys who've, landed stuff on the moon. So we had a great time. It was an awesome experience. And then that got around that I had done this talk to NASA about moon stuff. And so some of the conferences said, would you do that talk for us? And I'm like, why? Well, people like it. Okay, fine. No, I'm not complaining. And it's evolved. I mean, obviously, I've done a bunch of them now. I really enjoyed talking about this stuff. I am a techno-optimist. Typically, lately, I've been doing more newsy sort of, here's where we are now, we're making progress. This talk's going to go further than that. Because we do have a picture now of what becoming a spacefaring civilization actually looks like. And there are reasons to go to get better in space, starting with the dinosaurs died because they didn't have a space program, right? We have a shot at doing something about this. And in fact, we are. We actually have a planetary defense group. So it's not, this is mostly run by NASA, but ESA has a big role in it as well. And so this is a group of folks who specialize in dealing with existential threats to the planet. The obvious one to think about is asteroids, but there are others. Climate change falls into that ball of wax. I read a paper from them that actually led to another geek out, mostly about how to manage supervolcanoes. Now, our nearest supervolcano to us, anybody know? It was the last one to erupt. It's Taupo Lake in New Zealand. It's a supervolcano, erupted about 60,000 years ago. Their proposal to stop it from erupting again, if they thought it was going to, we're pretty good at volcanology these days. We can tell when magma is starting upwelling and the risk of a supervolcano, is to use geothermal power extraction to actually cool the volcano down, to actually pump cold water up against the magma well, take that power back and pump more water against it, and actually keep the crust hard enough that the upwelling goes away, rather than causing a major eruption and a disruption to the entire ecology of the planet. Interesting idea. But we're talking about the asteroid side because this is all spacey stuff. And we've actually made progress in this area, right? Has been the DART mission, if you were following along with this. DART was the intention to see, can we actually change the orbit of an asteroid? Given that whole science fiction thing of there's an asteroid coming to the Earth, what do we do? Blowing it up with nukes seems like a bad idea. Then you still have an asteroid hitting the planet, except it's radioactive now. Like, that's not this improvement. Can we alter its path? The mission was actually using a binary asteroid system, Dimorphos being the main asteroid, a bigger one, about 500 meters across, orbited by a much smaller asteroid called Dimorphos, but most people call it Diddy Moon because that's funny. You know, technologists are funny too. And they successfully launched this spacecraft to impact the smaller moon. This is actually an animation of that. This is a series of photographs taken by the vehicle, the impactor. It's about 500 kilograms, moving about 7 kilometers a second, straight towards that little moon. Cleverly, they actually, an Italian mission was attached to it, a pair of microsats that separated from it earlier so they could video it happening. So we are now like sending up digital camera crews for our satellites now. And so this is, here we go. It's a rubble pile. We're getting closer, frame by frame. You'll know the frame when it hit. Okay, there. Didn't quite finish transmitting that. So yeah, 780 meters across is Diddy Mouse. The moon was 160 meters. It was orbiting about 1 kilometer away. The orbit around that asteroid was about every 12 hours. The goal, so they hit it with 500 kilos at 4 kilometers a second. That's the moment of impact. That's those little Italian image captures, the Leica cubes. And so their goal was to change the orbit of the moon by about a minute. They were hoping for, if they could get a minute, they got 33 minutes. That's science. Surprise. Now, we're very aware that, especially in these class of asteroids, these S-types, they're mostly rubble piles. They're literally just collections of rocks. And so when you hit rocks, they hit each other. And so that effect had a much larger impact. It also sprayed out an ejecta stream of those rocks about 1,000 kilometers. Tens of thousands of objects came spinning off there. So there is now another mission called Hera on the way to going back to this asteroid, the binary system, to look at it again post facto. And asteroids are sort of the key to the whole thing. If we're actually going to get serious about functioning in space, we do need to get serious about utilizing resources in space. And these asteroids are our best option. They offer a huge array of opportunities. We'll get further into that along the way. There's an argument that we're in a narrow time window as a civilization. Right now, all of the unusual minerals and things that are necessary to operate in space are easily available, and we're doing it. But gradually, those minerals are going to become more expensive to extract. And as that price goes up and they're needed elsewhere, we're less and less likely to spend more time in space. And the NASA paper I was reading on this said, we got about 50 years. 50 years while these materials are relatively cheap for us to experiment on it, to get to a place where we can now extract those same materials from space for use in space and potentially on the Earth as well, before it become too expensive to bother, and we probably never will as a civilization. So I'm not used to the idea that we have a time limit on this, but there's a case. This is not that weird. There's an argument that the time for building transcontinental railways, whether you're talking about UK, Europe, the US, or even Australia, was the time when forests were especially plentiful because you needed all those rail ties. And that as forests became more scarce and wood became more expensive, it wouldn't make economic sense to do that. So that period in the 1800s where we built a lot of key railway, that was probably the only time we could have done that. And we may be up against that exact same constraint here. Okay, let's talk about the weird people in our world, which are the explorer types too. The other reason to do this, to get into spacefaring, is not only defending the planet and providing resources to the planet, but also a place to put the weirdos. Like there's a certain group of folks that need to explore, and they will explore even when it's crazy to explore. Yeah? You get the James Camerons, it's like, I'm going to build my own submarine and go down to the bottom of Challenger Deep. Yeah, good for him. I would not want to do that. That is a very small can in a very deep hole. But it's great that that's happening. And it's great that we have a society that not only allows that, but it somewhat celebrates that. It means there's an edge that we can aspire to. It's a place for those folks to go and bring new ideas back. It's an area for us to press against the edges of our technology and explore other things. By the way, the most important thing in this picture is the fact that that astronaut is kneeling, because you can't kneel on the moon. Your suit's inflated and you can't bend your knee. If you ever watch the videos of the Apollo astronauts walking around the moon, they do more of this, kind of the Michelin Man thing. So yeah, they think they have a suit design now that'll allow you to kneel. Makes it easier to look at stuff. First step, if we're really going to get serious about spacefaring, is getting into orbit. That's Heinlein's old quote. Once you get to low Earth orbit, you're halfway to everywhere. And that has changed dramatically over the past few years. For a long time, there's a belief that we'd never be a spacefaring civilization until we actually had space elevators. This idea that we would string a cable from the surface of the Earth around the equator all the way up to a balance point. It would actually be above geostationary orbit because you have to support the weight of the cable in the process. And I've done a geek out on this if you want to go look for it. It's called the elevators and tethers, because an elevator is just a tether that's in synchronous orbit and happens to be touching the ground. This is very unlikely to happen on this planet. Not only from a materials perspective, it is incredibly difficult to build materials strong enough. We've seen a few in experimental labs that would be tough enough to actually sustain this. But you also have a problem where not only have to build this incredibly tough material and make it absolutely solid, but you got to make it like 40,000 kilometers long and a bunch of it. But also you have to get up there. This is a long way. So if you hopped on an elevator and you hit the button, take me to space, please, you got to go 40,000 kilometers. So now if you're going 400 kilometers an hour, which is pretty darn fast for an elevator, you're still talking 4 days. Like, bring a lunch. Also, you're going to pass through the very thickest parts of the Van Allen belts along the way. Now, right now, we don't send humans above the Van Allen belts. They're hanging out in the space station, which is below it. The only time we ever did is when we sent those guys to the moon. And A, we sent them there fast. They went through those belts in a minute. And B, we sent them through the thin parts further off the axis of the equator to minimize their exposures. This would go right through the thickest part. We might do this for cargo. We probably wouldn't do this for people, but more likely we won't do this at all. Because we're getting to a place now where our chemical rockets may be fully reusable. Our buddy Elon, and it's hard to say that these days. You know what? I miss the guy who flew his sports car into space. Like, that was a fun Elon. This Elon's a nutter. But he still made this company. And we now take for granted the fact that the first stages of Falcon 9s land back on the Earth to be reused, coming close to 20 times each. He's done that more than 200 times now. It's trivial. He has more satellites in space than the rest of the world combined 4 times over. There's about 8,000 operating satellites up there, and like 6,500 of them are his. That's Starlink, right? And he's making money. That's now a profitable business for him. But this is the Starship. This is the experimental vehicle. It's only flown twice. Both have resulted in rapid, unscheduled disassemblies. More rapid than planned. The first launch was particularly horrendous. The third launch is maybe this month. It's coming. And the goal here is a 2-stage rocket that is completely reusable. The lower stage will turn around and fly back. Now, that's the second flight. We could see that perfect engine cone there. That's kind of a big deal because one of the arguments was the only time we've ever tried this many engines at once was the Soviet N-1 rocket, which had 30 NK-33 engines on it. And all 4 of those attempts blew up bad. And so there was you can't have that many engines, but apparently you can. But yeah, the flight profile is interesting. That the assembly takes off, largest rocket in history, 9 meters in diameter. And then after about 2.5 minutes, the upper stage takes off from the lower stage flips around, flies back, and lands. And if that wasn't weird enough, he's going to do it without landing gear because he's got a pair of giant chopsticks that are going to catch the lower stage. I can't wait to see that happen. The failure modes there will be quite spectacular. Then your upper stage goes up into space, does the work it wants to do, and then when it wants to come back, it actually belly flops through the atmosphere and then lands on its tail just like Buck Rogers did back in the day. And we wouldn't believe any of that, except he's done it once from 10 kilometers up and not at orbital speeds. So if this vehicle works, the mathematics for low Earth orbit changes. These are the only numbers you'll see in this entire presentation. The Atlas V is the old generation rocket from the 90s. Back in the 90s, if you wanted to fly a kilo in space on an Atlas V, it was about $25,000 per US dollars per kilo. When Falcon 9 came along, they found a way to reduce that price down to around $8,000. There's only a half a dozen of these rockets left. It is fully retired. It's being replaced by a rocket called Vulcan. Falcon 9 is the rock star rocket right now. If you have a choice of a payload vehicle on Earth today, you will fly with a Falcon 9 because it is the cheapest by a mile. There are some payloads that cannot be flown in Falcon 9, typically for governmental reasons. The Falcon Heavy is a bit of an odd rocket. It's nominally cheaper. Practically, it is not. And only for much heavier payloads do you bother with that. The Vulcan rocket is the replacement for the Atlas V. It has flown exactly once this past January. That price is an estimate in terms of the price per kilo. New Glenn is the rocket supposed to be built by Jeff Bezos. Yes, the Amazon guy has been trying to build a rocket for 20-something years. We have now seen the first flight hardware being driven around Florida, well, really around the Space Center. So hopefully they actually fly it. That number, price per kilo, is straight speculation. But it is a very large rocket, New Glenn. It's a 7-meter rocket. Not as big as Starship, but bigger than anything else. And that is interesting. The Space Launch System. So this is the reusing shuttle components to fly into space. This is the Artemis project, which they've flown exactly once. They're going to fly for a second time, supposed to be this year, now pushed to next year. They're going to send humans around the moon for the first time in 50 years in that rocket. It is catastrophically expensive. You may wonder why. Why would they fly this ridiculous rocket? Well, let's talk a little bit about US politics, because in the US, the NASA very cleverly made sure that when the space shuttle was operating, some part of the space shuttle was built and or maintained in every single state in the United States. So that there was a congressman that benefited by the shuttle. When the shuttle ended in 2011, all of those congressmen got a little tense. And so they said to NASA, you need to build a rocket using all the space shuttle stuff. That doesn't matter that it's a good rocket. In fact, I don't think they actually wanted to build the rocket. It was essentially a jobs program to keep all of those people working. The problem now is they've actually built the rocket. So now we're starting to see the price tag for this rocket. There's only one thing more expensive for lifting stuff into space than Artemis, and that would be the shuttle, based on the same technology. Current guess for Starship Super Heavy, the rocket I'm talking about here, depending on who you ask, between $20 and $100 a kilo. And that's a sea change. That's another order of magnitude decrease in cost. Now you're talking about being able to lift yourself into space for the price of a first-class airline ticket across the ocean. And that is pretty profound. That means we can lift a lot more stuff into space routinely, which opens the door to really building out some infrastructure. Now, the largest thing we've ever lifted into space is the International Space Station. It took somewhere in the neighborhood of 70 launches, a combination of Proton and Soyuz rockets, along with a lot of space shuttle lifts, about 35 space shuttle lifts. And we got about 450 metric tons of more or less working space station up there, capable of supporting 7 people, often as many as 11 people for some period of time. And if you're doing the math, Starship could lift this entire thing in 4 flights. So for a lot less money. Not that you would build another space station this way. In fact, this space station is getting very old. The first parts flew in 1998. It's been continuously inhabited since 2000. And now, almost 25 years on, it's wearing out. Parts of it are quite fragile now. It needs constant maintenance. The 7 main crew on the station now, 3 of them are engineers, pretty much full-time, just keeping the station running. The rest can do science. And so they want to retire it by 2030. Maybe they originally talked to 2025, then they were talking 2028. Now they're trying to hang on to 2030. NASA has a plan to make new space stations. They're not actually going to build them. They're actually now offering to pay for payloads. So the same way they commercialized resupply to the space station, which is what SpaceX made a lot of money from, was bringing supplies up to the station for a commercial contract. They're proposing the same thing for stations, where they're going to describe workloads they need to do in space, different kinds of research and so forth, and different companies can build and fly space stations to supply those workloads. One of the problems with having one giant lab in space is that the experiments interfere with each other. So certain classes of experiments, most of the time the International Space Station does microgravity experiments on humans. And so anything that would disrupt those microgravity experiments is a problem. So for example, we have done no experimentation with centrifuges, with actually creating artificial gravity in space. Not only is it difficult, but the process of operating a centrifuge would disrupt all of the microgravity experiments. But we could have a separate station for that. And so that's the idea now, is build smaller, more stations, more purposes. One of those could easily be a kind of hotel. Might be a bit rustic, be like a wilderness, like putting something up in the Northern Territory without a lot of support. It's like, you might get eaten, but maybe you'll have a good time. We don't really know. And this is the Bezos proposal, is this thing called the orbital reef. It's massive. That's where all of the space station components are about 3 meters, 3.5 meters in diameter. These would be 6 meter in diameter cylinders. So they're much, much bigger. That architecture would be several times the size of the International Space Station. Of course, it's just a mock-up. This is not real. We'll see if these get built. I think the coolest thing to come out of this experiment is this particular little dude here from Genesis Engineering. It's a single-person spacecraft. So one of the problems when you go and do a spacewalk is that in order for you to be able to move, you're basically, you're wearing a spaceship that's inflatable. And so if you were at normal air pressure, you would just be stuck like this. You couldn't move your arms. And so they put you into a low pressure environment that's almost pure oxygen. And so you have to pre-breathe oxygen to get the nitrogen out of your blood system. So the process of doing a spacewalk for 6 or 7 hours is half a day of prep. It takes 3 people to put 1 person into a spacesuit to get them to work for 7 hours. That whole, Mark Watney took a suit off and on thing in The Martian. Yeah, you're not doing that. You can't put a spacesuit on by yourself. It takes a lot of help. We need to get better spacesuits. And this little guy's a cool idea because he'd be running at space station pressures. So you basically climbing through the airlock of it, locking it up, pop yourself off, go to the site you need to do the work. And then you got your eyes on and potentially your manipulators to do the thing. And then you can go back. So it offers some flexibility. This particular station design from Lockheed Martin is supposed to be largely automated and man-tended. They just signed a contract with SpaceX to fly this entire space station in a single lift on Starship. Because you can. All right. And finally, last of these, Axiom Space has actually been flying people to the space station, just finished their 3rd flight. They are ex-NASA space station people. And this inner component here, they want to add it to the existing space station. That one right there is under construction now. It's almost finished. Their goal is to build a 4-part space station attached to the International Space Station that then will detach once the space station is being retired. And NASA is so interested in that, they're actually talking about the laboratory modules that'll be attached to it going with, because they're much younger. They probably have another 10 years of use out of them. So we may not see the International Space Station just go away. The oldest parts are 20 plus years old and mostly Russian. That we'll keep some of the American parts and add them to a new station that'll separate off. Interesting idea. All right, so space stations are one thing. Let's talk about the moon. I like this picture, and I want you to be as skeptical as I am. Whenever you see a cool picture of space, you should say, Who took that picture? Because if you notice, this is a picture of the Earth with the moon in front of it. That is the far side of the moon, not the dark side of the moon. You'll note it is lit at this very moment because the sun is shining on it. And that's a tricky place to take a photograph from. It is actually a photograph. It was taken by this Discover satellite. The Discover satellite is a sun observation satellite. It sits at the Earth-Sun L1 Lagrange point, a stable gravitational point where it essentially orbits at the same rate that the Earth does, sitting between the sun and the Earth. Normally, its job is to look at the sun. It actually gives us solar weather, gives us a warning if there's going to be a major magnetic anomaly or anything like that. But somebody was clever enough to put a telescope on the back of Discover pointed at the Earth. And it is a telescope because Discover is 1.5 million kilometers away from the moon, or from the Earth. So the Earth is very small. And it routinely takes pictures of the Earth in full color and sends them back. So we have these great current disk shots of the Earth. And every so often, the moon whizzes through the frame. And I do mean whizzes through the frame. And in fact, it's not a color camera at all. It is a single monochromatic camera, but it has filters. And so in order to make a color picture, they actually have to take 4 photos. They take the black and white photo, then a red, then a green, then a blue. It's one of the ways you know this photo is real, is that if you look close, right there's a bit of a green halo. Because the green photo is taken last, and the moon moved. I mean, CGI guys are good, but that's going above and beyond, right? Anyway, I love this picture of the moon. It's just a reminder the moon's a whole thing, and it moves around. Obviously, Americans went to the moon already. That was the Apollo project. The Apollo project, was a military project in disguise as a science project. It was to demonstrate that American democracy was superior to Soviet communism. It worked. Exactly 12 humans walked on the moon. They are all white men. 11 of them are military test pilots. One of them was a scientist. This one, right there, that's Jack. Jack Schmitt was a geologist. He was supposed to fly on Apollo 18, but they canceled Apollo 18, so they moved him on to Apollo 17, which surely upset somebody. But that meant we put a geologist on the moon. For 3 days, 3 7-hour missions, total about 22 hours, we had a geologist on the moon. Jack had a good time. Jack likes rocks. That's Jack. You'll notice Jack is dirty because Jack was on his face a lot while he was looking at the rocks. All of this, by the way, you can watch on YouTube. They've published everything about Jack being up on the moon. And Jack did dangerous things on the moon to look at rocks because he was a geologist, and geologists really, really like rocks. We have the only photos of a human's face on the moon are Jack, because Jack found that the gold foil eye protector that went across his face shield interfered with him looking at the color of the rocks, so he kept raising it. Now, that shield was there for a reason. The sun is so powerful without an atmosphere, it would burn his retinas out in a moment. Jack doesn't care. Jack's a geologist. Jack likes rocks. And so you can hear over and over again Capcom saying to him, "Hey, Jack, when you get a sec, can you lower your visor?" Which is NASA speak for, "Close the frickin' visor, you idiots!" So Jack got so frustrated with this that he started putting paper into his helmet. That you can see on the side of the helmet there, that's a little made-up sunshade. So on your left arm, when you're an Apollo astronaut, is the step-by-step instructions of everything you're going to do on every spacewalk the whole time you're out there, page after page, minute by minute. And as those minutes went by, he would rip them out and stick them in the side of his helmet so he could look at rocks. When we put these weird humans, these scientists, in a place where they can learn something new, they will do anything. We've only done it once, 22 hours. Imagine if we could leave them up there for a month. What would they find? We've never done that. We only did this one time. And he was crazy. Let's get 4 of them and give them a month. Biggest problem with the Apollo space program, why we ultimately stopped it, was this vehicle, the lunar lander. It's an extremely dangerous vehicle. There's a bunch of failure modes in it that if any of them had happened, we would have lost the crew. There was no way to rescue them. They only had 3 days worth of supplies on the moon. It takes more than 3 days to launch a rescue mission. So they were going to die. And in the end, because this was a military mission to prove superiority, screwing it up with a bunch of deaths wasn't worth it. And the Nixon administration shut the program down. They took the leftover parts and they made Skylab, but ultimately they wound the entire initiative down. They poured all their money into shuttle because that was going to be the less expensive way to space. It turned out to be the more expensive way to space. As the shuttle ended, Dan Golden, one of the NASA administrators, said, if we had not done shuttle and just kept flying Apollo, we would have flown 6 Apollo missions a year, plus 2 to the moon each year for the same money. Anyway, we're now going back to the moon with Artemis. The Australians are involved. You guys are building a rover. The first mission's already flown, Artemis 1. This was an unmanned mission to test the Orion capsule. The Orion capsule doesn't have a working life support system. You kind of need one of those. You're going to put people on it. But it did allow them to do a bunch of maneuvering in space that no one had ever done before. So we've got a lot of models for how to maneuver in space using gravity tricks and so forth that no one had actually exercised. Well, this mission did exercise a bunch of them. We did some really clever flying tricks. So it wasn't a complete waste of $4 billion. Artemis 2 is the next mission. This is going to be a replay, essentially, of Apollo 8 from 1968, where they're literally going to send a crew of 4 around the moon and back again in a free return trajectory. So even if stuff breaks down, they will at least burn up in the Earth, not be left out there in orbit. At least figure out where you're going to land the bodies. Hopefully everything works fine. They're going to be able to come back there. I mean, one of the things you have to understand about flying back from the moon is the moon's gravity is very low. It's only 1/6 of a G. So as you're departing the moon, that little bit of thrust you need to fly away from the moon's gravity, you're moving about 2 kilometers a second. Sounds fast, but wait. As soon as you're going fast enough to get away from the moon, you move back into the Earth's sphere of influence. And the Earth is greedy. And you will go faster and faster and faster and faster. And by the time you get to the Earth, having done nothing in terms of thrust, you're moving at 18 kilometers a second. And so that's why that big old heat shield's there. And we have to be very careful about our techniques for re-entering so that we can dissipate all that energy and heat on an ablative heat shield rather than just burning up. And one of the things that was shown in Artemis 1 was the heat shield didn't do as well as it should. It didn't fail. We did get the capsule back, but it had problems. And so there's revisions being done. And it's one of the reasons they postponed this mission. The third Artemis mission is going to be the return of humans onto the moon. There's a proposal for building a space station. I don't think we're actually going to do that. But we do need a lunar lander. And unlike in the Apollo missions where we wanted to build it, we had a very dangerous lunar lander that launched with everything else. They're going to fly the lunar lander separately. And they put out a tender contract for building a lunar lander. And SpaceX won it with a version of Starship. So the reason that SpaceX won it was not only was it a reasonable proposal, but it was relatively expensive because they're building Starship anyway. Elon looked at it, this is a bit more money to continue building Starship, which is great. He did some fairly clever design ideas like don't use the bottom engines that'll dig a big hole in the moon, but actually put a set of engines high up on the hull that'll help you with your landing. The problem is it is 16 meters tall and the bottom 3/4 of it are tank. So the people are at the top. So if you want to get, from here where you are down to here, those are the people down there. You kind of need an elevator. Like, watch that first step. Also, better find a flat spot because you're landing a skyscraper. It's really a large vehicle, but it should be 100% reusable. They can refuel it. And it should be able to carry 100 tons of cargo, which is astonishing. Way more than anything else even could possibly do. The problem, of course, is that in order to make it work, you're going to have to refuel it. The current, this only shows 4 refueling missions. Looks like it's 10. Now, it's a fully reusable spacecraft. That's not that bad because it's not going to waste a lot of money. And in fact, it's kind of silly to draw it this way. Like you're going to lift the lunar lander up into orbit and then you're going to fly tankers to it one after the other, sort of meet them like that. I'm sorry if this makes people uncomfortable. I mean, it's sad to even show it. We've never done in-orbit refueling before, ever, for anything, ever. This would be new technology. And there's a problem here because you need to have all the fuel sitting at one end of the tank where the pipes are. You can't have it floating around, and it does float around. This is a video from inside of a Falcon 9 while climbing into orbit. So you can see when the thrust stopped. That's what happens to liquid oxygen as you're no longer pressing against it. You can't pump that. So you have to accelerate the vehicle to settle the fuel and the oxidizer enough to be able to pump it. But when you accelerate a vehicle in orbit, you change its orbit. So there's some tricky bits to be done here to figure this out. But it also speaks to other infrastructure we could be building. I find this picture inappropriate too. Let's move on. This is the best idea I've seen so far. So you got to fly 10 refueling vehicles worth to fuel up a lunar lander. So you build a little infrastructure in space that you can dock multiple tankers to. You can now rotate this structure to set the fuel and pump it. It's just a whole lot more efficient than actually pushing vehicles around with vernier thrusters. This also speaks to an idea of infrastructure. Now you can put out a price for fuel. I don't care where you get your fuel, but if you get some, bring it here and we'll pay you for it. So, Starship is one way to get fuel, but another way to get fuel would be, say, from asteroids. So when we talk about becoming a spacefaring civilization, it's about having way stops, having refueling points, having infrastructure to make it easier for others to operate in space. This is one of those way stops. It's not a new idea. This is from the 1980s. This is using an Atlas V. This is a proposal from Lockheed Martin to do the same thing, to be able to store fuel in orbit, although they were talking about storing liquid hydrogen. That's a liquid hydrogen tank with a sun shield to try and keep it from evaporating. Liquid hydrogen is a terribly difficult fuel to work with. It is extraordinarily cold, 6 degrees Kelvin, as opposed to the 90 to 100 degrees that you get with liquid methane and liquid oxygen. It's also only a liquid in a 6-degree temperature range, below which it becomes a solid and above which it becomes a gas. And it suddenly expands rapidly and bursts your tanks. So it is tough to keep cold. It has to be kept stunningly cold, but not too cold. And, if you make a mistake, the whole thing gets destroyed. So be careful. Liquid methane is now more popular as a fuel, and you've seen this being used more and more, including in the Vulcan rocket and in Starship, because it basically stays cryogenic at roughly the same temperatures as liquid oxygen. Liquid oxygen is so cold that if you run a pipe of liquid oxygen near it, it will freeze the liquid oxygen solid. So you have to put insulation between the two. You don't really have to do that with methane and oxygen. So there's our lander, very tall. We could reuse this vehicle, which is kind of cool. We just have to keep refueling it. And that has its own challenges. And now we can actually back to this picture of them being able to kneel. The vehicle in behind doesn't exist, obviously. It was one of the proposals for a multi-stage lander. It actually is a 3-stage lander. They had one stage just to get it to the moon, then you threw that away. And then you had a 2-stage piece, and you can see the 2 parts there. This is the landing stage, and that is the ascent stage. So when you're done with your moon exploration, you leave this on the surface, and that goes back up to your Orion capsule so you can go home. Which makes it tricky to build a base, because it's like you drive a car to the base, and then you leave the car there and get another one each time. Like eventually the parking lot will be full. Our current proposals for actually putting a base down on the moon are on the South Pole, particularly in the Shackleton crater. What's interesting about the Shackleton crater is almost directly on the South Pole. There are parts of it that are continuously in sun, good for solar power, and parts of it that are continuously shaded, so good for ice, which is our product. We want to get oxygen from the moon. And here's a picture of Shackleton crater over the course of a lunar year. And you should ask the very important question, who took this picture? This is a composite of photographs from the Lunar Reconnaissance Orbiter. Every time it passed over Shackleton crater, it would shoot a photo. They then composited it into a single timeline to show how some of the crater rim parts are almost continuously in sunlight, while the inner part of the crater is continuously shaded. And that crater is way bigger than you think. 21 kilometers across. You can fit a few Sydneys in there. And they figure several billion tons of ice down there. And ice can be split into oxygen and hydrogen. And that gives you breathing gases, as well as a component of your rocket fuel. And that's important because up until now, every time we've done anything in space, we bring literally everything with us. Every breath you're going to take, everything you're going to eat, all of it you have to carry with you. It's what makes it so expensive. The prospect that we start using the resources up there so we didn't have to carry it with us changes the equation. It's what makes us spacefaring, is that we can, at least partially, live off the land. We do have challenges with navigation around the moon. This is an ESA proposal called Moonlight. That is a small constellation of satellites, maybe about 16 of them, that would both provide GPS-like effects, so you know exactly where you are, because you can see 3 of those satellites at any given time, and cellular communications. Right? Well, all the Apollo missions landed on the near side of the moon so they could stay in contact with the Earth. In fact, we've never landed anything on the far side of the moon. Only the Chinese have. The Chang'e 4 lander is back there, and in order to communicate with it, they had to put up a satellite sitting at the L2 point beyond the moon to be able to relay data back to it. So infrastructure, put up a set of satellites so that we can communicate anywhere. And that means your radio equipment is lighter and less expensive. And your navigation systems are cheaper and less expensive, and lighter. So your vehicles become more efficient. This is what Elon thinks a base on the moon would look like. I think it looks like Burning Man. And not particularly practical. Actually, it kind of looks like Space 1999. You remember that? If you're old enough, don't ever watch those. Your childhood memories of Space 1999 are vastly superior to the actual show. I found a torrent and I watched a couple of them and it made me sad and I stopped watching them. So yeah, far more likely it's going to be Igloo-like. This is actually from the original ESA proposal that I read back in 2017 that led to this whole thing in the moon base and so forth, where they take an inflatable habitat with a rigid airlock. They soft landed on the moon. They then use robots to bury the main body in regolith to protect from radiation so that humans can survive there for at least a month. By that point, you've probably taken enough radiation that you should go home before things get bad. Not very sexy, but practical. Another option is the skylights. So one of the things Jack Schmitt taught us is there really was volcanic activity on the moon. He's the guy who found the unshocked piece of olivine. Which if you're a geologist is all like, holy cow, that's amazing. But it was proof that there'd been volcanic activity, that actually volcanoes had erupted on the moon. They didn't build cinder cones because there's not enough gravity and not enough energy, but they did those the big flat spots on the moon are lava flows. And as the moon cooled and the lava retreated, it left behind massive tunnels, some 2 or 3 kilometers in diameter. And every so often, those tunnels are close enough to the surface of the moon that over time they collapse and create these things called skylights. This is the Marius skylight. So that drops a good 500-600 meters down, and then it goes in. We don't know how far. We've never really explored it. There's proposals to put a vehicle down in there and start looking around. But the idea is that if you need to be protected from radiation, well, there's a ready-made tube. So you put your inflatable down there, you slide it inside, you inflate it, and it gives you your protection. Again, not sexy, practical. Although you do have a good Dr. No effect of, flying up out of a hole in the ground. A lot of robotic works are going to be done there. We have found that regolith, which is this fine silicate, can be heated with a laser to become a fairly sturdy solid. So it's good building material. So we can see automated machines doing a lot of construction for us. This is one of the proposals for the Gateway station, which would be orbiting the moon with humans on it, is that they could help operate those robots in close proximity rather than having to do the 2-second relay from the Earth. It'll be easier to operate them that way. Although our machine learning model is getting pretty good now. I think you could pretty much write a piece of software that said, build a wall, and it would build it for you. We have to get into this idea that we can extract resources from other bodies. And the moon's a great place to start. It's almost a perfect training ground. It's only 3 days away by rocket. And it has got a ton of interesting minerals on it. So can we prospect on the moon? Can we find useful ore bodies? And then can we extract them and refine them? And can we make a product on the moon? Would we want to make a product on the moon? Well, we now know that the moon contains an awful lot of silicates, silicon, iron, calcium, titanium, magnesium, a lot of these transition metals, phosphorus, aluminum, sulfur, some rare earths, thorium and uranium are found in certain deposits we believe are actually asteroid-based. We could make solar panels. We have all the ingredients. And in fact, contemporary solar panel construction methodology is largely based on growing crystals. And the biggest problem with growing a crystal is gravity. So reduced gravity might actually help us build better crystal. Imagine buying superior solar panels because they were made on the moon. Now, one argument is we'd make them on the moon and use them on the moon. There was even a proposal to say, why don't we just paint the equator of the moon with solar panels, which seems a little nuts. That would be basically making enough solar panels to go from LA to New York to go around the moon. Total land mass of the moon is roughly the size of the United States. Probably not that practical. Better idea. Solar power for the Earth, space-based power. So, make your factory, build your solar panels, build a linear accelerator, take those panels, load them up, fire them back into space, back to geostationary orbit around the Earth. And you can see that's the little space-based power module. That is what's known as SPS alpha. It's the idea that we can make solar power in orbit and beam it back to the surface of the Earth. It's big, 5 kilometers across. It's a lot of solar panels. Just because you're in space doesn't mean you get a lot more solar. It's about 1,300 watts per square meter of solar energy in orbit, as opposed to about 1,000 for us down on the Earth with atmosphere. And now, of course, we only get 1,000 at noon on the equator when the sun is directly overhead and it's a perfectly clear day. But you would always get 1,300 watts per meter in orbit. So geostationary orbit, you can make about a gigawatt of power out of that. You then send it down to the surface with a microwave transmitter. So that would be about a 10-kilometer across array. The energy density of this is not high enough to like cook birds in flight. But you probably want to put a fence around this. It's not a place to walk around. On the other hand, it's a gigawatt of 24-hour-a-day base load energy with no environmental impact on the planet. Compelling. This is one of the Bezos' keen ideas. There's no innovation here. We know how to do all of this. We already transmit electricity with microwaves routinely. It's not unusual. So the only problem is if you're going to lift that many solar panels from the Earth, it costs $100 billion. It's an impractical power supply. But if you're building them on the moon, it takes a lot less energy to put them back into orbit around the Earth. So the costs drop dramatically once you have the infrastructure in place. Also, you don't have to just beam the power back down on the Earth. You can use it to move vehicles around. It's an energy source. Every spacecraft, in order to propel itself, has 3 things. It has an engine of some kind, a propellant of some kind, and a power source. So normally we think about chemical rockets. So we're combining liquid methane and liquid oxygen, and we're combusting them in a chamber that accelerates rapidly out the back, and that moves the rocket, right? So our power source is the chemical energy of those 2 fuels, and the fuel and those 2 fuels are also the propellant. So it's actually the force of it moving out the back that moves the rocket, and the engine operates it. We've also made Hall effect thrusters that are electrically powered. We put on great big solar panels. We have a little tank of xenon, which is a very dense fuel, and we superheat the xenon and accelerate it out the back of the ion engine to move it. If we want to scale that up, they're pretty low powered. We really need a huge amount of electricity, more than solar would make sense. Things like nuclear reactors. Well, those are heavy. Well, what if we took the power plant out of the equation? What if we had space-based power transmit the power to the vehicle? So now you're just carrying the fuel and the engine. So you can imagine a vehicle that's transferring resources, say fuel, between the moon and the Earth. And instead of having to have that ablative shield to handle reentry, you don't want it to enter at all. You want it to go back into orbit. You use this thing to beam power onto it to run its engine to slow down enough to go back into orbit. You transfer fuel, you give it more power, it accelerates back out to the moon, picks up another fuel load, goes again. It's a bus with a stationary power plant, right? The same way that we have electric trolley buses, where we make the electricity elsewhere, and then the bus has the wheels and the motors and an overhead cable connected. So in this case, it's a microwave or a laser transmitter. Infrastructure in space. There's also an idea of just use a laser, create a big reflector, and you can accelerate a vehicle this way. Sounds like science fiction. It's already been demonstrated to work. And so once we start building this kind of multi-gigawatt power sources in orbit, we can use them for power on the planet. You can imagine for emergency services, an area like a major earthquake happens, to be able to come in with a set of vehicles, lay down a receiver, and provide power for that area during the crisis. Useful, but also can move vehicles around. All right. Main thing the space station's done for us, I'm going to just involve humans in space a little bit here, is it's taught us about how humans do in free fall. And the answer is poorly. We typically allow astronauts to stay in orbit for about 6 months. It takes a year from them to recover for that 6 months. Their feet hurt because they haven't walked on them in 6 months. Your feet are really used to being walked on. If you don't do it for a while, it's a problem. Your peristaltic systems, blood pumps, breathing, digestion, all of that works in free fall. That's fine. Burping doesn't work. You have to plan for burping. There's a great video from the space station astronauts. It's like if you really need to burp, you have to back up against a wall and then accelerate yourself. The food all settles, then you can burp. And if you get it wrong, you have to clean it up. One thing that doesn't work is cerebral spinal fluid. So inside of your brain is a pair of organs that produce a fluid that clean your brain, essentially. And that fluid then normally, through motion and gravity, goes down into your spinal cord where it does blood exchange and is removed in your urine. When you go into free fall, that fluid builds up in your head. And if you'll notice, and you look at the astronauts in the space station, they're all a bit puffy. In fact, the fluid builds up so much in your brain, it presses against the backs of your eyes and it bends them. So the other thing you'll notice is that all the astronauts on the space station are wearing glasses because their eyes don't work correctly anymore. And that's problematic. It does damage to you. The astronauts have to exercise 2.5 hours every day to lose bone mass slowly enough to be recoverable. So think about an idea of the flying to Mars in free fall. It takes 6 months to get to Mars. You spend 6 months in the space station. When you land, there's a bunch of people there to carry you out so that you can spend a year in rehab to be back to normal again. It's just not practical. We could try and get there faster. We could find some supermen who are going to do it. Like, listen, test pilots are aliens. Like, they're crazy. They would do it anyway. Like, there are always astronauts that are willing to do that, and they try and find a way to make it work. But we could do better. We know that we can make artificial gravity by creating a rotating structure. It's just a question of how much gravity we need to make. The challenge is the rotating structure has to be big enough that you don't have Coriolis effects, real Coriolis effects, not the toilet swinging the wrong way around, which, okay, we get a lot of that gag, especially when you're in Australia. But the real Coriolis effects is if I'm standing in a rotating structure and I turn my head while that structure rotates, like your vestibular system goes bananas. So it has to be big. And this is roughly the graph for it being comfortable. In order to have 1 g of gravity, you're talking about a 50-meter diameter structure. That's big. Biggest thing we've ever flown up there was like 6 meters. So there's some big experiments to be done. Also, can we reduce the amount of gravity? Mars is only 1/3 of a g, 0.3 g, so that would be much easier. But we don't know how well humans would do in 1/3 of a g. But you know what we could do on the moon? Leave a guy up there for a year. That's 1/6 of a g. We'd learn a lot about how a body would function in 1/6 of a g that way. Good experiment to do on the moon. We've talked a lot about building rotating spacecraft. This is a proposal called Nautilus X, largely using space station parts plus an inflatable rotating cylinder. The Martian had an excellent one, the Hermes, where it was a segmented structure. So they actually just had like containers, 4 of them, on the rotating structure so that you would be able to sleep inside that rotating structure, or at least do some of your work in gravity and be comfortable that way. There's a problem with this whole idea, which you still have to transition to free fall routinely to do work on the spacecraft and so forth. And virtually every human that has ever been in space is sick for the first day they're in free fall. So you can imagine being in a vehicle where every day you transition from working in free fall to being back under 1 g or 1/2 a g over and over again. Does that just mean you're nauseated the whole time? Excellent. Or would people get used to this? Humans are remarkably tolerant. We don't know. All these experiments need to be done. We're not there yet. That's about as much as I want to talk about humans. Let's talk about the more robotic stuff, although I think we're going to need humans involved in this as we learn, just because human eyes and human bodies are incredibly good at exploring this. So mining asteroids is sort of the key thing to building up resources. A, it allows us to make more stuff in space because we don't have to bring it up from this gravity well. B, it allows us to provide the Earth with expensive things that are getting harder and harder to find off of the planet. There are lots of different kinds of asteroids, tons of them. The most common kind are called the C-class or carbonaceous asteroids. have a large amount of water in it. And water would be the first resource we'd want to extract, because water can be made into oxygen and hydrogen, which is rocket fuel, as well as breathing gases and other potential uses. Although these also have nitrogen, potassium, phosphorus, a number of other components that would be useful for making soils and other components. This is the Mathilde asteroid. It's one of the better photos we have of asteroids relatively close. There are many different kinds of asteroids. Many of them are rubble piles. This is probably actually a rubble pile. We just weren't close enough to be able to identify the individual rocks. S-types are silicate types. This is another photo of Deimos and Dimorphos, where we did the DART experiment. So S-types are silicates, so high in different kinds of silicate compounds. They also have a fair number of rare earths in them, so yttrium, praseodymium. They're good valuables that we use in the semiconductor industry. And then the mother of all asteroids, the M class, or the metallics. So this is nickel, iron, platinum class metals. This is the stuff that's supposed to destroy our economy if we pull it out. The rough estimate of the value of everything up there is somewhere in the neighborhood of 10,000 quadrillion US dollars, okay, which is like a whole B-1 bomber. This is 16 Psyche. This is, of course, an artistic drawing of 16 Psyche. The real picture is just sort of a blurry blob. We last year sent a mission to 16 Psyche. We actually believe that it is a planet core, that there was supposed to be a planet forming between Jupiter and Mars. You may have heard this in school back in the day, and that's why there's an asteroid belt there. It's the tidal forces of Jupiter ripped it apart, but it's had enough time to form that a lot of the heavier metals collected in the center, and this is that center. So we want to explore it. It's filled with metals. It should likely have some actinides as well, uranium, thorium, those sorts of things. We have never really looked at it, but we're at the cusp of this. We can imagine the potential to go up there and to do mining from there. So we've already prototyped and played with vehicles that could do this. This is TransAstra's Honeybee mining vehicle. So they built pieces of this, and they want to go up and collect small asteroids, 50-meter ones. This was the asteroid return mission during the Obama administration that got canceled, where they basically take sunlight, concentrate it, and use it to superheat the rock and evaporate out the volatiles and then vacuum them off into storage tanks. Doesn't make sense to move asteroids around. A, heavy. B, takes a long time. C, easy to weaponize. So rather go to them and take the valuables out of them, separate them off, and then send back the valuables piece by piece. So obviously, water is a big one, but also all of the silicates, some of the transition metals. We can make bigger versions of this. These, again, prototype pieces. So collecting a larger asteroid and then being able to collect these individual pieces. There's an argument that they'll start doing factory work right from here. If we learn more about doing zero-G manufacturing, which we can do in LEO with all those commercial space stations, learn to manufacture valuables from there. So again, rather than moving the raw materials around, you make your stuff where you are. But we're on the path to doing this. You reduce the cost to orbit, which we're well on doing, you can actually fly this stuff and start to extract resources from asteroids. And when you can do that, now you can send them back down to Earth if that makes sense. Some materials it will, some they won't. So those are simple deorbiter vehicles and land, and you can use those resources. Most of them you're going to want to keep using the moon up in orbit. So stop flying the heavy parts from the gravity well that is Earth, bring them from easier places. The moon's one, but the asteroids even more so. And you can start doing larger assemblies of construction up in orbit. So we're building up infrastructure. We've got refueling depots. We've got power generation sites. Now we have larger construction sites, places for people to be, to stage more exploration and extraction missions. I mean, where does it ultimately end up? What's the next logical step? We get to the O'Neill cylinder. This feels like science fiction, but I hope I've built a path for you to see this is just the next level of construction. Either we take an asteroid or just materials that we've extracted, and we construct a cylinder roughly 5 kilometers long and 1 kilometer diameter. We rotate it at a 1.5 RPM. So the interior surface is 1 G. The horizon will be a bit wacky, but there's room for a couple of million people in there. So you got to build a stable ecology, not easy to do. But if you want to go to space, you take an elevator. You go back to the center, and off of the back of it, there is your space station, right? The space station's out here. So that's where you can launch from with no gravity. But on the inside, You have your gravity well, your solar collectors. We have enough material in the, just out of the asteroids alone to build something like 50 or 100,000 of these. Room for several trillion humans. They can stay in the same orbit as Earth, roughly following the same track. It actually makes more sense to move a little further in, not as close as Venus, but closer than the Earth. You'll get more solar power from that. There's actually fewer asteroids in that realm, so it's sort of a safer place to be. And people can be fruitful and multiply. There's an argument of you can turn the Earth into a garden world. A lot more room, a lot less resources needed to be extracted from the planet. It's not possible for us to move a huge number of people up there. You know, just even that big spacecraft's only going to move a few hundred at a time. So you're not going to move millions. You might move a million eventually, but it's not going to be hundreds of millions. It's not going to be billions. But birth rates are falling here anyway. Opportunity to move up there gives you new opportunities, you know, to be more likely to have more folks there. We're going to top out as a civilization around 2050, maybe 2100. The population will actually decline. We create these frontiers for other folks who want to do new things to go to. They'll populate up there and we'll build more of them. The planet will do better. And we'll all be a bit more comfortable. And then we can go further. I'm just outlining the simple steps. We have most of the pieces to getting here now. We just have to choose to spend the time on it. A couple of parts that need to get done, but go a little bit further. It's just not that far away. We might see most of it. I hope we do. And I hope this was fun for you. Thanks. The shows that this were based on are the Geek Outs. So if you go to geekout.show, it'll take you to .NET Rocks, and there's about 100 of them. There is an asteroid mining show. There is a space tether show. There's a bunch of other space shows if you want to listen to them. And these days, once a year, I do a 2-hour recap on space and a 2-hour recap on alternative energy. Those just came out in January. Have a good lunch.